Did it start again?
Yep, we're good.
Yeah, it'll only do 30 minutes at a time, because otherwise the class size will get too big. So. Okay, and then the last entry is going to be negative of a plus b minus x plus y. So I'm literally just adding the entries. And then the lower left corner is d plus z, e plus w, and negative of d plus e minus z plus w. So you just add it together. You don't even have to turn on your brain. You just add it together, slot by slot. Now what do you need to do here?
Make sure that it has membership in
Make sure that it has membership in S, which means make sure that its rows still add up to 0. Do they?
Yeah.
Do you need to show me a lot of work to convince me of that?
No.
Something.
This is just basic addition, right? If you come over here and you just simply write element of S, and you have to write that. Some people are still not writing that on their solutions. That the conclusion is that the sum of your two vectors is an element of S. I'm going to believe that because I can add those up, and I can see that those rows add up to 0. You don't have to convince me that you know that. That's not what this class is about. Yeah.
You wouldn't have to mention about A, B, D, E, X, Y, Z, and W being element of R.
Being real numbers?
Being real numbers.
No, I mean, that's kind of the overriding assumption is that every entry that we ever see is going to be in the real numbers. If A, B, X, Y, D, and E, and so on were not real numbers, we wouldn't even have matrices that were in the large vector space of V. And that's kind of not something we want to deal with. So that's totally fine.
Okay.
I mean, it is possible, like, if somebody's really picky, they could expect you to write that down. But that to me is just in the background here. The key thing is the form of the matrix. And the form is correct. Yeah.
It's the same thing with the constant k then, we don't have to put every time that the constant's in the real numbers? Or?
Right, although I do, so that comes up in the second
Oh,
part. I
good.
do like people to introduce their variables when they, I like to know where they're coming from instead of just appearing out of nowhere. So for the closure under scalar multiplication, the way I would like to start this would be to say the following. Let capital A be as above. That way you don't have to write it down again. So you just take one vector that you used before, and so you could write k be a scalar. I typically will just write k as an element of the real numbers just because it's shorter to write that than to say all the words. Okay. So then you just have to calculate k times a, and that just means we're just going to take ka, kb, negative k of a plus b, and then kd, ke, and negative k of d plus e. And we just look at that and we ask ourselves, do the rows still add up to 0? They clearly do. So this is an element of S. So important to write element of S there. I will take off points if I don't see that. That absolutely has to be there. The conclusion is that you've got a result that is an element of S. Okay. If we want to be really good about it, I don't necessarily need you to write this down, but this is helpful, is to just say, since closure under addition and closure under scalar multiplication hold, S is a subspace of V.
There goes that.
Or just put A1 and E2 accent.
Yep, you can use A1 and A2 if you don't like, yeah, either notation is fine.
Yeah.
So it's a subspace. Does anybody know what the dimension of this subspace is? This is not on the sheet. I'm just curious if anybody knows what it is. 6 would be the dimension of the whole vector space V. Why is it 4?
Because there's only 8.
There's 4 variables here, right? 4 free variables. So it's a 4-dimensional space. Actually, you want to see something kind of interesting?
No.
Yeah. Really?
You don't?
Yeah, no, yeah, I do want to see something interesting.
Okay. Okay. Here's the interesting thing.
I couldn't resist.
Once you know it's a subspace, so this is a very common question I might ask you. Part A is prove that it's a subspace. Then part B is find a spanning set for it, or find a basis for it. And part C would be find the dimension of it, right? So you get asked all those questions. But if we kind of jump ahead and we before we even check the closure under addition, if we actually notice that S could be spanned by looking at, how do you find a spanning set for a set of matrices, or for a set of vectors? Well, you represent the general vector, which would be, this is like a general form, which we needed to do for this proof, but we also could think of it as being useful for finding a spanning set. So we write down the general form here, and then we say, okay, bust out the variables, right? And what you'll have then is that S is the span of 1, 0, negative 1. So you bust out the A, then you bust out the B, right? Then you bust out, I guess I didn't use a C for some reason. So the next one is D, that would be 0, 0, 0, 1, 0, negative 1. And then bust out the E, and it's going to look like that. You guys believe that? So your set S actually can be viewed as the span of the, because this matrix can be decomposed into a linear combination of these four. It's A times this, plus B times this, plus D times this, plus E times this. Right? So those four matrices do in fact span S. Right? What I want to point out to you guys is very important. What I want to point out to you guys is that once you realize that S is really this, then you actually know that it's a subspace through the back door. Because anytime you have the span of a set of vectors, you have a subspace. So in some sense, if you have done this first and just said, hey, by the way, notice that S is really the span of something, that justifies that it's a subspace. Okay. So then you don't have to do this proof, you see. Of course I can, but of course you do need to know how to do this, because I might say, is it closed under addition? Is it closed under scalar multiplication? I would want to see you show me those steps directly. Or maybe you won't be able to represent your vector in a way that you know how to bust it out or something like that. So it is important to be able to do this. But are you guys following me over here?
Yeah.
Okay, so that just makes your life a little easier. And then these guys are going to give you a four-dimensional vector space, right? Be careful to not say yes too quickly. If I have the span of four vectors, four things in this list, does it mean it's got to be four-dimensional?
No.
No, because why not?
Linear combination.
The variables you busted
Might
out.
not be LI.
That's the point. It might not be linearly independent. The set of vectors might not be linearly independent. So what you would do, what you would have to do would be to put these, to test these for Li, right? Well, how do you test a set of vectors for Li? You put each vector into the columns of another matrix. And this other matrix that we're writing down is like a tool for testing for linear independence. So this first matrix, if I just kind of write it down in this order, right? 1, 0, negative 1, 0, 0, 0, and then this one would be 0, 1, negative 1, 0, 0, 0, and this one would be 0, 0, 0, 1, 0, negative 1, and that one would be 0, 0, 0, 0, 1, negative 1. Augment with a 0 vector. You would need to make sure that there was a pivot in every one of these first four columns, because if there wasn't, then that would mean there was a linear dependency. So you have to row reduce this. You notice the first two rows are already good.
Yeah, you can do it.
And
You
clearly
cancel
you
the
can
third
move the, you can get these two over here, and then this one will be zeroed out, and this one will be zeroed out. So it'll be fine. So, but for example, what if one, let's just imagine, this isn't true, but what if this column right here didn't have a pivot
Then it
for
wouldn't
whatever reason?
Is it consistent?
LD.
Then there's a free variable exactly associated with this third column. What it really means is that there are many ways to cancel these four matrices out in a linear combination. There is a linear dependency there, and so your dimension is not 4, It's something less than 4. And so what you'd have to do, what would you do if I asked you then to give me a basis? Suppose I asked you to give me a basis for S. And you know that these 4 matrices are a spanning set for it because they span all of S just by the very nature of this equation. They do span S. S is their span. So they span S, but they're not linearly independent. So how would you get a basis?
Take out one of the vectors.
Which vector, Sergio?
The one, the free variable.
Right, whichever. So if this was an unpivoted column, for example, you would wipe it out so that now there's no unpivoted columns. Wiping out that column is just like wiping out that vector, right? So you've thrown it away, and the 3 vectors that are left would now be your basis, and it would only be 3-dimensional. This is all hypothetical. It's not true in this case. In this case, you do get a pivot here. You do want this matrix, right? But we've seen a number of examples like this, right, where we put our vectors into the columns. We know that they span our space. So we put those vectors into the columns to try and uncover any dependencies that might be there. Just to remind you, linear dependence is a lot more than just one vector being a multiple of another. If you see that one vector is a multiple of another vector, then those 2 vectors are certainly LD. But you don't always see the linear dependencies because they could involve a number of vectors, right? It could be difficult to detect it. So you really do have to put the vectors into the columns of this matrix and row reduce it. By the way, I see people do this too. Okay, so another no-no. So you work this out like this. You get these pivots here. You say, linear independent, right? So the people will say something like, this is Li. And that's not what you mean. A matrix cannot be Li. We don't talk about a matrix being Li or LD. We talk about a set of vectors being Li or LD. So this is my set of vectors. Right? That can be linearly dependent or linearly independent, but not a single matrix. Okay, so somebody's going to say that, and I just don't want it to be any of you guys. Okay, are we kind of good on that? Oh, good. So problem 3C, I already did it. Find a spanning set for S. We just did it. Okay, I'm going to jump over problem 4 for right now and go to problem 5. Problem 4 is pretty easy, is the reason. Just row space, column space, null space stuff. I think you guys pretty much know how to do that. So my goal is to hit all the important types of topics first, and then we can always go back. Okay, this is a good problem. Number 5. I have a linear transformation from P2 of R to M2 of R. And T of 1 is the matrix -1, 2, 0, 0. And T of x plus 1 is the matrix -3, 0, 2, 1. And T of x squared plus x plus 1 is 3, -2, 0, 1. Okay, so here's the question. Compute T of ax squared plus bx plus c. In other words, find the formula for T of any arbitrary quadratic. Okay. One of the things that is so important in chapter 4 about bases for vector space is that if I tell you how the basis gets transformed, and here's this is actually a basis. I don't know if you guys, would you be pretty well convinced that this is a basis for P2? What would you do to convince me of that? I'm just curious. This is not the question at hand, but I'm just, the side point. Why are these 3 circled things a basis for P2 of R?
Put it in a vector. Vector matrix.
The dimension is 3. This is 3, and how many things do I have here? 3. So it's the right number. So they're either both or neither. And We just know that it is? You know, let me give you a quick, I can tell you why they're linearly independent really easily. Clearly the first two are not scalar multiples of each other. So if I just only looked at the first two, they would be Li. But the third one isn't going to create any dependencies because I can't write the third one in terms of the first two because the first two can never hit x squared. Right, you take linear combinations of 1 and x plus 1, you're not going to get something with an x squared in it. So, therefore, these are all Li. Of course, you could test it for Li by putting them into the columns of a 3 by 3 matrix. The determinant will be non-zero, right? It's kind of like what we did before. Whenever you have the right number of vectors, whenever k equals n, you're going to be able to build a square matrix out of that, right? And it'll all come down to just the determinant of that matrix. It's actually really simple in that case. If the determinant's not 0, then it's yay, everything works, it's a basis. If the determinant is 0, then it's neither, right? So it's one way or the other. So anyway, these guys are a basis for P2 of R, and just based on telling you those three things, supposedly we can now find T of anything in the whole space. Does anybody know why? Say that again? Well, just based on these three givens, this one, and this one, I claim you can write down a general formula for T of anything. This is assuming that this T right here is linear. We're going to assume it's a linear transformation. I know we just learned this stuff, it's pretty recent. This is very similar to some of the, I don't know if you've all done the homework for tomorrow yet. It's similar to some of the homework that you're working on for tomorrow. So I just, not a bad idea to just go over it now.
We would find T of x and T of x squared?
Right, if I find out what T of x is, and I find out what T of x squared is, you see, remember that a linear transformation respects scalar multiplication and addition. So if I want to know T of this whole expression here, I can actually bust it out because T will respect those operations. So I can take the A out, and it's A times T of x squared. And then plus B times T of x, plus C times T of 1. So I actually already gave you T of 1, right? I didn't give you T of x directly, but I claim we can find it. You guys know how I can find T of x?
Take T of x plus 1 and subtract T of 1.
Exactly, exactly. So, have you done the homework yet for Monday?
Not all of it.
Not all of it, but you certainly sound like you know what's going on here. So
Maybe a little bit.
that's why I was wondering. So yeah, so basically T of x plus 1 is just T of x plus T of 1. Respects addition, right? So I can figure out what T of x is by taking this one minus this one. Agreed? It respects addition and basically also subtraction. So T of x is just T of x plus 1, which was negative 3, 0, 2, 1, minus T of 1, which was negative 1, 2, 0, 0. We just subtract those and we're going to get negative 2, negative 2, 2, 1. Okay? So that's what T of x is. So I'm solving for this one. I was given this number and I was given this matrix and I was given this matrix. So I'm just subtracting. So it says this one goes here, this one goes here, and I just subtract. Clear enough? So I know what T of x is. Why do I want to know what T of x is? Because I'm going to need it right here. I'm going to need it right here. So I've got T of 1, that was given. I now worked out what T of x is. Does anybody know how I can get T of x squared?
X squared
Same
plus
thing.
x plus 1 minus x plus 1.
This one minus this one. Exactly. This one minus this one. So T of x squared is just, let's see, 3, negative 2, 0, 1, minus negative 3, 0, 2, 1. That comes out to 6, negative 2, negative 2, 0. Okay.
Can you say that again? How do you get T of x squared?
I got T of x squared, actually I can maybe put it here. See, t of x squared, t of x squared plus x plus 1 is just, if I just use the fact that t respects addition, that equation is true. Why did I break it up that way? Well, because I know this one, that was given to me here. And I know this one, because it was given to me here. So I can find this one by taking this one minus this one. That make sense?
Yeah.
Okay, so now I've got all three of these matrices here. So let me just go ahead, let me just put the answer over here, I guess. So t of ax squared plus bx plus c is just a times the first matrix, 6, negative 2, negative 2, 0, plus b times the second matrix, which was negative 2, negative 2, 2, 1, plus c times the original value of t of 1, which was negative 1, 2, 0, 0. That make sense so far? Anybody have any questions about that?
So we need to put the A and B in front of those matrices.
Yeah, because you see them, they were busted out over here, so they're still here in front of those matrices. Now, you could leave your answer like this if you wanted, or if you wanted, there would be nothing wrong with just compressing it into a single matrix. So the upper left corner, you know, you have 6A minus 2B minus C. That would be fine. Right? And then the upper right corner, this is not necessary. Now, I'm perfectly fine with the previous line, but this is just in case you want to see it a different way. The upper right corner would be what? Negative 2a minus 2b plus 2c. Good. The lower left corner would be what? Lower left corner? Negative 2a plus 2b. That's it, right?
Yeah.
How about the lower right corner?
B.
Just b. Oh, that's a general formula. So we derive that general formula from these three values here. Okay? Question, go ahead.
So, A and B and C will be given to us on, because,
I could just ask you to leave it in terms of A, B, and C for general variables, but I don't actually have to tell you. I might say something specific like find t of 5x squared minus 8x plus 16. I could ask you that, and then you know what A, B, and C are. But there's no reason why you can't just do it very generally here.
oh, okay, because on one of the examples I was like, where
It
did
might
we
have been
get that?
specific.
It's like 6 and 8, okay.
Yeah, it could be very specific,
So
but
we
this
don't
is
have
like
to
the general.
go look for it, you'll either give it to us or.
Right, I'll tell you what
Okay.
I'm looking for there.
Yeah, sure.
Okay, I have a question. How many of you guys watched my video that I put up last night? So about half of you maybe? Okay. There's two more parts to this question which have to do with what's on that video. It's what I'm going to talk about tomorrow in class. So I'm trying to decide whether to go over it or not.
Yeah, go.
I think I will.
Yeah.
I think I will. Okay, so I'm gonna, the key thing we need for the rest of this problem is actually the formula that I just derived over here. Okay, so I'm going to basically get rid of some of this right here right now so we can have enough room to write the rest of it. Okay.
The 1-to-1 part, we're skipping that for this.
Yeah, that we don't need to worry about, but kernel and range is what I want to get into here. So basically, the kernel of T, I'm going to give you the very brief version here. At first, I'm not going to go into a lot of depth with this. The kernel of T, anytime you have a transformation, so T is always going from V to W. And I like to draw, this is the picture that you'll see on the video when you watch my beautiful video. Basically, one thing we know for sure about a linear transformation is that the zero vector has to map to the zero vector. But there could be other vectors that also get mapped to zero. potentially, and all of those vectors that are getting sent to 0. Just as an example, if your transformation is take the derivative, if that's your operation, take the derivative of a function, then any constant function is going to get killed to 0, right? So whichever vectors the transformation kills from V makes up the kernel of T. So this is visually what the kernel of T is. So when I write it over here, it's just the set of vectors B in V such that T of V is 0. And notice I'm putting 0 sub V and 0 sub W to kind of keep them straight. So it's just those vectors that get killed by capital T. Now, I'm going to save this for tomorrow night, but you guys could do it if you want for practice. It's very easy to show that that is a subspace of V. This little piece here, the kernel of T, is a subspace of V. So that would require you to check closure under addition and closure under scalar multiplication. Okay? Not hard to do that. If T of V gets killed and T of V prime gets killed, well then T of V plus V prime is going to get killed. It's going to preserve addition. So I'll show that to you tomorrow because that has to go in the formal notes. The point is it's a subspace. This collection, this subset of capital V that gets killed by the transformation is a subspace of V. If it's a subspace of V, we're going to start going to our usual questions. Find a basis for it. What's the dimension of it? Blah, 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 blah. All that good stuff. Okay? So, how do you find the kernel of T? You're looking for which inputs get killed. So, in this problem, our inputs are the quadratic polynomials. We're looking for which quadratic polynomials end up getting killed, which means that they end up resulting in the 2 by 2 matrix of all zeros. So would you agree that to find the kernel, I basically need to just set this equal to 0 here? 0, 0, 0, 0, and solve it? That's what you have to do. Set this equal. If you just want the easy, basically you start from here. This creates an equation for you. T of V is 0, solve for V. That's really what it is. Okay, if T of V is 0, solve for V. So basically, on that example, what you would have to do, so in our problem, in our example, what we would do is we would take T of ax squared plus bx plus c, which we've now calculated already. I'm just recopying it again. 6a minus 2b minus c, and then negative 2a minus 2b plus 2c, and then minus 2a plus 2b, and then b. That's my output. And what you do to find the kernel is set this equal to the 0 vector of w, and in this case the 0 vector of w is just my 2 by 2 0 matrix. And what you do is you go and you solve for which quadratic polynomial is going to give me that. But you see that that's actually not too hard to do. You're basically setting each corner of this matrix equal to 0. Right? Now, normally, when I'm setting each corner of my matrix equal to 0, I'm actually creating another system of equations, aren't I? I'm basically, this has to equal 0, 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 and you end up with 4 equations, and you create an augmented matrix, and you solve it by back substitution, more EROs, right, all the stuff from chapter 2 again. In this case, you probably can eyeball it. Because, and maybe that's what we should do so we don't get sidetracked by the EROs, but you can see that B has to be 0. Going